We'll give it a couple minutes for people to join in. Okay, so it's been 2 minutes, but I was expecting there to be a slightly bigger crowd at the beginning, but that's okay. Maybe people were sleeping in or didn't realize that when I said that we were meeting Tuesday, that I meant this Tuesday. Or maybe I should have just been more patient. So the first thing that I should probably say is that I am recording these Zoom meetings, and I'm planning on posting the recordings onto the website that I made for the seminar. So if there's something that goes on, or if you're like, hey, I want to review what Jacob said for this thing, then that will be available to you. And you kind of have to start with the recording statement. So, hi, my name is Jacob Garcia. I'm now a 4th year, which is crazy, PhD student in the math department. I'm going to be, the phrasing that I've been using is leading the seminar, because the way that I envision the seminar is that it's hopefully going to be you all driven, because you all are the people who have to take the qual at the end of the summer, right? I'm just here to like maybe try to like find good problems or talk us through solutions or like remind us of like things that you knew or maybe didn't know, depending on how this last year of instruction went, and to kind of give you an outside perspective of like how these quals normally go and like maybe how you should be studying and things like that. So if we were in person, I would just be like talking to you all, and on Zoom this is more awkward, but I kind of just want to like hear from you all, like how's your summer been going, like just like how are you on like a holistic level, like are you feeling good, is your summer like a happy experience, are you miserable in the heat, right, like what's going on, and then also like how are you from a productivity studying for qual standpoint, like did you try studying 1 day a week and that didn't work, or have you been studying every day? Are you like studying has been really good until I hit differential topology, like like so I could start. My summer's been great. I just got back from a camping trip with my wife, which is really nice. I'm doing a virtual conference right now, and virtual conferences are the worst. I don't know how anybody gets anything out of virtual conferences. And I'm studying for my oral exam, which is like the written qualifying exam, but different. So Anybody who would like to take it away, feel free.
Sure, I'll go. My summer's been good. Just kind of been at home for most of it. Visited my girlfriend in Columbus, which was cool. And then I feel like studying has been going all right for me. I've mostly been focusing on algebraic topology because I don't think I learned much in that class. So I've just been going through the book and the notes, and it's been going well so far.
Cool.
I'm Zach. My summer on a holistic level is going pretty well. I just like last week moved down to Riverside, and like the room's all set up now. I'm getting to know the area. And when it comes to studying, I've actually been pretty similar to Ryan in that I spent most of my time going through part B. Like I've just been trying to like do a somewhat thorough work through of Hatcher's book, and I'm like in the middle of the covering spaces with the homology left. Otherwise, like part A feels really good and part C feels pretty good, but part B still scares me.
I guess I'll go. Hey, hey Jacob, my name is Shanna, and I actually like the online conferences way better
Okay.
because I can just like be in my peace. Sometimes those get a little crazy. Like I can like hang out with my animals, so I love it. And in the trees, you know, that's me. Unless it's like MSRI, which is in the trees, and it's perfect. Or like IAS, I'm digging it. So I'll be a first year, so I'm just jumping in this, you know, kind of like a crazy person. But I did. It's interesting to see, you know, when people are scared, it's because like the class didn't go so well or something. So I understand. They know I sort of sat into some things. So I feel you on part B. So, but Jacob's a wizard, and I'm sure he could teach us part B in like 5 minutes. So I think we're going to hold you to that. I'm in like 8 summer programs right now, so I honestly haven't looked at much of this. But as soon as I don't know, I've heard really awesome things about you, and I think if we all work together, we'll get through this. You know what I mean?
I do not know what I've done to get this undeserved praise, but I'll take it.
I think if you saw part B, you would feel for us. All right.
Oh, I took part B with Schultz. Not online, but I took it with Schultz. I can only imagine. Yeah, when I took it, we were asking him questions about his directory, and he was very proud of the fact that he had, and I quote him, moving pictures. So I can only imagine.
Oh my.
Oh yes.
All right. And my summer's going great, and I'm finishing up like I don't know, a second book that I'm writing. I like to write books, so okay.
Nice.
I guess I'll go next. My name is Daily Tamal. I'm technically in the year above Jacob, but I took some time off. So I think I technically, like units wise, fall into his year. I took topology my first year coming in. So that was like 2017, 2018. And I took it actually with Fred for A, Schultz for B, and Viduzzi for C. So same professors, but a little switched. So yeah, I have the experience with Schultz, but it's an experience to say the least. So I'm definitely, yeah, it's been a while since I've done topology, but I really like it. So I wanted to do that for my qual. And it's been a good summer. It's been an interesting summer. Holistically, I got to go to Disneyland, which I was excited about, do something fun. Yeah, so studying wise, I've been like really trying to, I started with applied, and then I was like, I want to just focus on one. And I found out that Schultz taught part B. And so I was like, I'm taking topology. Because Schultz taught part B. So yeah, I decided to just focus all my time on topology because I knew that like I could definitely pass at least the part B part and put all my time into making sure that I get A and C down for sure. So yeah, it's been a while. I'm very, very rusty after a break and very rusty after like a couple of years of like not doing topology. So yeah, but I'm excited. I know like Jacob and I used to talk a lot in office hours. So like you said, Shayna, he's a very good teacher. Um, I've seen it firsthand. So I was super excited when he was like teaching this. I was like, yes. So yeah, we're in good hands for sure.
So I don't know if Jennifer was here when I said this, but if you could just like say like how your summer's been going, both from like a happy, holistic you level and also on like a how studying is going level, maybe like say a sentence of like who you are, that would be nice.
Okay. Sorry, I kind of wake up late and just got here. Apparently summer went very well, and yeah, but I still have to move over there because next quarter we're doing in person and everything. Well, I took topology, probably also interested in doing topology, so it's kind of makes sense for me to take the topology call. But yeah, I guess that would be it. Did I miss
Right.
anything?
Nope, that sounds great. Is that everybody?
I'll go.
Oh, okay, great. I was just
Okay,
like,
you
wait,
go
I can't
first,
remember
you
if Anthony went.
Vidur, do you want to go first?
No, you go first, Anthony.
Okay. Well, I'm Anthony. I am a third year. My summer's been going fine. I mean, second COVID summer, I guess. So I guess we're all kind of more used to it at this point. And, you know, the heat makes it so that we're all staying inside anyway. So I don't know. As far as studying goes, I've been mostly focusing on part C because that's where I feel weakest. This time, this is my second time, just for the record, taking this qual. This time I'm focusing more on using Lee as the textbook for part C as opposed to Berker and Janich, and I find Lee to be a lot better. I just think it's much more clearly written and has a lot more like sanity check type examples. So, but other people might find Broken Janich to be more their style. But yeah, so that's been going well. Other than that, I hope everybody's keeping well in their own sphere. I'm still like in the process of waking up, so sorry if I'm like I got my coffee though, so could be worse. So I'll be quiet now.
Okay, I'll go then. So I'm Vidur, and I've been doing the past year course of the past year remotely. So I hope to make it to Riverside by September. And I've been studying for the quals, but I've not looked at a lot yet. So part A is fairly good, I think. Otherwise, the summer's been fairly good.
Sorry, I think you cut out a little bit there. I heard you say that part A was good, and then you said I think, and then there was a pause, and then you said otherwise summer's been good. And I'm just like, oh no, the meat was lost. Fiddle.
Yeah, that's actually true. I said part B is okay, but I can't really say good. And C is the hardest for me. I understand C the least as of now.
Right. So cool. Well, thanks everybody for introducing yourself and saying hi. I'm really excited for this summer and what we're doing. Oh, just in time to not miss. Hey, Dan, hope you're doing well. If you could, I know that I'm putting you on the spot as soon as you join, but if you could introduce yourself and say like how you've been doing this summer, both from like a how are you? Have you done anything fun? Are you feeling good? And also from like a how has studying been so far? Have you been like hitting your milestones, or has it been hard to focus, or whatever? Maybe also like introduce yourself for the other people in the room. The guy is working outside for me. Maybe you didn't hear me, Dan. You there?
Yes, I didn't hear you though.
Oh yeah, if you could just like introduce yourself and tell us like how your summer has been going, and also like how you're feeling about topology, that would be great.
All right, fine summer. Very interested in topology, particularly algebraic topology or geometric topology. Yeah, no, that's about it.
Okay. Great. Well, thank you all for introducing yourselves. Okay, so before we get into math today, and for today, I figured that we're going to be spending like a chunk of time on introductions and talking about like how the course is going to go. And also when I sent out the interest survey, part A was what most people said they felt most comfortable with. Right, so I was like, okay, if I dig a little bit into the part A time to do this kind of stuff, then that's fine. But I am prepared to do math today, and especially if it's one of the like 17 problems that I'd labeled as part A between the mock qual and the problems you should know document on the website. I hopefully remember how to do all of those problems so we can talk about them. But there are some where I might be like, oh no, why did I put this one on the document? I don't know how to do it. But even if I don't, we can figure it out. Okay, so does everyone still have access to the website? Have you all seen the website? Do you have that bookmarked or something? Okay, then let me find the website and maybe send you all a link. Put that in the, okay, so there it is in the Zoom chat. So this is a website that I set up for our course. It has links to the homework sets from all three parts from this year, the lecture notes and the exams from all three parts from this year, all the old qualifying exams from last year's qual all the way to like the 80s, the website to the qual prep seminar for last year, which was run by Jonathan Alcaraz, who's absolutely incredible, trying to fill his shoes is a daunting task. And I also have two additional links that don't fit in those other categories called, one of them is a exercises you should know link, where I just like compiled a bunch of what I think are informative exercises for each of the three parts. Some of these are probably exercises that you got for homework at some point, especially for Fiduci, because Fiduci is very good at asking good questions on his homework sets. It's like some of those exercises are like, hey, the entire point of this exercise is for you to look up a definition. Just like remind yourself what this word means. Some of those problems ended up being like, I put them on there being like, ooh, this is a good problem. I should like I remember this problem as being a good problem. And then I like started looking at old quals and I was like, huh, that was a qual question. So, and some of them are just like ones that I think are interesting. But yeah, so if you don't know where you should start, doing a bunch of those exercises, I think is good, not that I'm biased. And I also put a mock qual 0 and I sent that out and I called it mock qual 0. But that's actually the 2019 qualifying exam. That's the qualifying exam that I took. And the reason, there's two reasons. The two reasons that I chose that qual is because one, that was the last qual written by this exact qualifying exam committee. So Vidusi wrote part A of this qual, Schultz wrote part B of this qual, and Wilhelm wrote part C of this qual. So to me, I feel like that this qual is a pretty accurate representation of what your qual is going to look like, and like the kinds of questions and the difficulty level that these professors tend to ask. Did everybody here attempt to take that qual? Okay, so if you haven't done that yet, I really recommend that before we get too far into this, like by the end of the week or before we meet next Tuesday, right? So maybe sometime over the weekend or next Monday or something, that you actually try your best to set up a 3-hour block and take this mock qual before you look at it. So hopefully if you're looking at it now, you can close it and stop looking at it so that you don't get spoiled for too much of the qual. And this does two things. One, it gives you a benchmark of where you are now, right? Okay, if you don't, so you should have access to all the Google Drives. If you don't, I can change the sharing settings. The sharing settings are supposed to be accessible as long as you're under your UCR Gmail. So if you look at the top right of your screen, if you're in a regular Gmail address instead of the UCR email address, then maybe you don't have access to it. But I can also go and change the sharing settings and see if there's something that I can do differently. Are there people who can't get it? Okay, so Anthony has access to his personal. Okay.
Yeah, me too. So I'm just in my regular Gmail. It's working fine.
Okay, yeah, it says. Okay, I'm not sure why, Zach, but we can troubleshoot that in a little bit. Okay, yeah, so the first one is that it gives you a benchmark, like where you are and like what you need to do. And the second one is that it just like puts you in the position of potentially having spent 2 hours on problems and thinking that you have made all of the headway that you're going to be able to make on these problems. And then 15 minutes later being like, wait, can I try this? And then, right, like it's amazing what you can pull out when you are just staring at the paper, right? No, there's nothing else that you can do but stare at the paper.
Jacob, may I
So-
say one thing on the exercises you should know? I don't have
Yeah.
access to that one. So that's the only thing I can't just pull up.
Okay, let's see what my share settings. Okay, yeah,
Those
for
are
this one, it
mostly-
says anyone with their R mail,
Right.
but I can change that to anyone. Blink. Cool. Okay, now try.
Okay. Wonderful. Thank you.
Okay, great. Yeah. Okay, so yeah, so I'm pretty familiar with this qual because I took this qual. I did well in this qual. So, and there's only one problem on this qual where I'm like, I have half an idea of how to do the problem, and the rest of them are just like, yeah, I can do this one.
I'm sorry, did you say because I came in about 3 minutes late. Are we going to be going over the answers to that one first, or the exercises, or like what's kind of the vibe and the structure that we're going to do? 'Cause that qual looks good.
That is a fantastic question. So the way that I foresee this qual seminar happening is that I'm really hoping that it's going to be you all driven, right? That for the first 3 weeks, we're going to try to focus on like part A for the first week and part B for the second week and part C for the third week, right? Just as like a way to like structure what we go over first. And, you know, there are some worksheets that Jonathan made for last year's qual, which some of those problems, I'm like, these are nice problems. Some of those problems, I'm like, I don't know about those problems, mostly because I can't do those problems. So yeah, I'm suspicious, but that's a me problem, not a you problem. And so I was thinking that for the first 3 weeks, I will try to come up with stuff for us to talk about. We might spend like 1 day each week going over some problems that I've compiled specifically for that day, and then 1 day each week with you all telling me what problems you all want to talk about, and we'll try to talk about those kinds of things. After those 3 weeks, I'm planning on writing another mock qual, right? The second mock qual, and you can either take that one like a qual, or you can just use that as an excuse to do a lot more problems, right? And after that, we're gonna recheck in, and we're gonna see what kinds of topics you all would like to talk about and where you all think we should focus. And if you're like, hey, like this one aspect of part C, or hey, like homology in part B, like how do I actually calculate some homology, right? Like, then we'll be like, okay, cool, let's talk about that. But I'm not going to pretend to know how the last year of classes went, because I didn't take those classes, and I'm not going to pretend to know like where you all are. So I'm really gonna trust that you all are going to be active participants in this seminar, right? And tell me what you all want to do, right? And then we'll try to do that stuff. So for today, I haven't planned anything specific in terms of math, but I'm prepared to talk about math, especially stuff in like the exercises you should know doc, or maybe we should save the questions in mockball 0, so that way some people who would like to take that as an actual qual have the opportunity to take that as an actual qual. Yeah. Okay, cool. Then the last thing that I like to say is like, how much should you be studying for this qual? And you should probably be studying more than you think you should be for this qual. Back when, we got to study in person, the way that I and a bunch of other people studied for their quals, and I took 2 at the same time, right? I took topology and algebra in the same summer, but we went to campus early at like 8 to beat the heat, and then we'd just stay on campus and work till like 6 also to beat the heat, right? And one thing that I think is extremely useful is to try to study with other people. I can't tell you how useful it is to work with other people on these problems, and to do stuff with other people, and to really like use that as an opportunity to like motivate yourself to do work, right? And also it's just great to buddy up with someone who like says that like, hey, they say that, right? Hey, I'm strong in part B. They just mentioned that they would really like to go over part B, but I'm weak in part C, and they're strong in part C, so maybe we should buddy up, right? Or, or maybe if you're taking 2 quals, you can find someone who's also taking one of the other quals, the same other qual that you're studying with. And this is what I did. I was like, I know topology, but algebra is so hard. And I found someone who was like, I love algebra, but topology is so hard. We just buddied up all summer, right? And we just alternated days. And on algebra days, he chose what problems we were going to work on that day. And on topology days, I chose what problems we were going to work on that day. And that's how we got through the summer. But it's amazing how much more work you do when you have someone else that says, hey, wait, do you want to do this problem before we leave? And you go, oh, all right. And then, you get like an extra hour studying, which you didn't think you were going to get in. So highly recommend working with other people and studying with other people. Obviously your mileage may vary, and I know that that's much harder over Zoom, but I would really encourage you to try to find other people. I've sent the last couple of emails out, not with you all like BCC'd, so that you can see the list of other people who are studying for the topology qual, so you can use that as a resource to like reach out and find. Okay, cool. That was all of the bookkeeping that I had on my impromptu, wrote this 5 minutes before the class started, list of things to go over. So if you all have any questions, oh, there is one more thing that I should say. Okay, so, and I'm going to tell you all the broad, this is how this qual committee works. Daily, I think that setting up a group me or Discord or some kind of group chat would be excellent. Feel free to include or exclude me as you all see fit. Okay, so the way that this written qual tends to go. Vidusi is an open bag. He will ask you anything that he has covered in the last quarter, including stuff about like the profinite topology of groups, which he spends like 1 day going over, and then that'll be on the call, and then he'll be like, what? I don't remember this definition. And yeah, so like you just kind of have to have like a really broad overview of part A. Schultz has asked variations of the same 15 problems for the last 15 years. Okay, you can win Schultz's qual by just studying a list of problems. And if you know how to do those problems, you can pass part B. And anytime Schultz asks something which is beyond that scope, he always puts a hint after the question that tells you how to do the problem. It's very clear. Like, you can get by through part B quite easily because of the way that Schultz writes quals. And Wilhelm, so a lot of people are like, part C is really hard, and the way that Wilhelm teaches these topics makes it very confusing. But the way that Wilhelm writes problems is that he has like a question bank of like 45 questions, and he always just chooses 3 of those 45 problems. Or like for his final, he chooses like 15 of those 45 problems or 50 problems or whatever it is, and asks you those. So when I took the qual, all 3 problems were just 3 problems from my final exam. Last year, 1 problem was directly copied from that year's final exam. 1 problem was 2 questions from the final exam put into a part A and part B of 1 question. And the 3rd question was a slight variation of a problem from that final exam that did not actually change the solution. It just made the question look different, but the actual solution was entirely the same, because he just replaced a compact domain with a different compact domain. And that's the only difference that he did for the problem. And the fact that the domain was compact was the only thing that was important. So there is a way to study for these quals that is totally independent of learning the material, right? And so I think that you could do a lot worse for studying for part C than just looking at this year's final exam and just learning how to do all of those problems, right? Like that, yeah. So I'm going to start off by saying that, and I'm going to be peppering those final exam problems into our workings out, just so that way we can see a bunch of those problems. But that's like the overview, just so you all know that like this is the kind of stuff that's like if you all were in person and talking to like more people who are more senior who had taken this exam and like did things like this, that this would be common knowledge. But because of Zoom and being online and stuff, like this is not stuff that would be as readily available to you unless I like said it explicitly. So I'm gonna say it explicitly, and hopefully none of the qualifying exam committee watches to half an hour of the first video. Right. I'm not promising that Schultz or Wilhelm are going to do what they did for the last couple of years and follow what I just said. But I'm saying that anytime that you note a trend, right, you should make note of that and use that as a useful bit of information. Okay, so I think that is actually the last thing that I was going to say when it comes to bookkeeping. Do you all have any questions for me about this summer, how the summer's going to go, or about the fall, or should we try to start talking about math?
I would like to start talking about the math, but I don't know what everybody else wants to do.
Let's do it.
Okay, cool. So, part A, what do you all want to talk about? Is there anybody who's been doing some part A problems or have been looking at this exercises you should know sheet and being like, wait, what's up with this problem? Or something like this?
For part A, I've been working through like Moncrief and like the path connected stuff, like, oh, it just threw me for a loop. So I know on your like exercises to know there's like the few like 5 and 6, there's a few path connected problems. But honestly, I would be down, or like even just like number 1, like I would be down for like any of the problems on this list. But yeah, those are like always ones that I super struggled with just to wrap my head around originally in the class.
Kind of like what Dali's saying, yeah, like anything about coverings or profinite topology, right, that I'm seeing on the part A. Yeah, coverings are like problem 10, 11, anything kind of down, you know.
Okay,
Yeah.
cool. So
Yeah, coverings too.
Mm-hmm.
I love things. So let's
Yeah.
see, I heard, okay, so like 5 and 6, I heard 1, I heard 10, 11, okay.
10,
Oh yeah, the list of,
the parallelizable, that looks kind of hard. Number 10.
Oh my gosh, yes, that one was such a, oh, that was
Yeah.
such
oh,
a,
you mean for differential topology?
Oh, I'm sorry. On the exercises you should know. Yeah. Oh, oops. I didn't see that. Okay.
Yeah, you're on the last page, but that's okay.
Sorry.
Okay, so the reason that I put number 10 on this list is because you can solve that question without knowing what parallelizable means.
Oh.
Yeah.
Okay, so just an A. Yeah.
Yeah.
Actually, all of them would be helpful, but whatever people think. I bet you have cool ways of doing all of them, anyway.
So I actually really like number 5, but the reason that I like number 5 is because the person that I was studying with for the topology qual kept forgetting this result. Like every other week, he would be like, wait, why is this space path connected again? And I'd be like, Joe, we've been over this. So I've ended up proving this question like 12 times during the summer that we were studying for this problem or something. It's like, no, you should prove this now because you got it. Okay, so I'm totally down to start.
4, because 4 is also about
Oh, did you say 4?
Like those are both.
Oh yeah,
connected.
4.
8
Yeah,
is also a
4.
covering, so like 8, 9, 10, 11, things like that.
Oh yeah, 8. All right.
All those things.
9, you said. Okay. All right. So this is just a list where we are excluding 2 and 3. Oh, and 7, I guess.
like all of them, just all of them.
All of them. All of them. Okay. Okay. Well, since I just said how much I like number 5, maybe we should talk about number 5 first. Because 5 definitely, in the list of like things you should know, I definitely think that this is more on the side of thing you should know as opposed to like thing that I like. So because Schultz loves talking about connected and locally path connected spaces. That's how he likes to give you topological spaces for part B. But like the fact that you are globally path connected is often a very important aspect of whatever it is that you are doing. So yeah, you should really just know that when you see connected and locally path connected, that you are just path connected, that you can connect any 2 points with path. So how do you do that? Okay, so let's, for contradiction.
Jacob, I'm sorry. Are these notes going to be posted or should we be writing what you write?
So I've never been able to, I can try to post these notes.
Okay, that'd be great.
But I'm also recording the video.
Okay.
And I'll post the video.
Okay, all good.
Yep. So for contradiction, we're going to assume X is not path connected. Okay. And then I'm going to introduce some notation here. So notation, just to make it a little easier to see what's going on. If there exists a path from A to B, we'll say that A is related to B. This is an equivalence relation on X, by the way. So why is this an equivalence relation on X? Well, every element is related to itself by a constant path. You just map an interval to a point. That's a continuous function, so that's a path, right? If A is related to B, there's a path from A to B. If you take the reverse path, you have a path from B to A. Right? Right. A to B, if I'm going this way, hey, here's a path which goes in the other direction, just flip the arrow. Right? And concatenation gives you the transitive property. Right? If you have A, B, C, I can make a path from A to C by just concatenating the path from A to B with the path from B to C. So this is an equivalence relation, which is nice. Okay, so now what I'm going to do is I'm going to define U to be right, I can't. So let's see here. Right, so there exists X and Y in X such that X is not related to Y, right? That's what it means to be not path connected, right? There's not a path from X to Y, right? Now I'm going to define a set U to be the set of all Z and X such that X is related to Z. So what am I doing? Here I have a picture of my X. I should move this bit of the Zoom window so that we have more space. Okay. I have X and I have Y over here. And I'm calling this open set, this set U, because I'm going to show that it's open in a second. Right? But somehow there is a barrier which is stopping paths from getting from X over to Y. And then let V be equal to X set minus U. Okay, so I just set up a set U and a set V, right? U contains the point X and V contains the point Y. What I'm gonna want to do is I'm gonna want to show that these are both open, disjoint, and that they cover X. So by construction, right, these are disjoint. Full sentences, Jacob. Note U and V are disjoint, and U union V equals X by construction. U is a set, V is the complement of that set. So they're disjoint and their union is all of X. So the only thing left for what I want to do, right? The goal here is to show that U and V are both open. They form a separation of my space, and that contradicts the fact that my space is supposed to be connected. So let's show that U is open first. So to show that U is open, we're going to let Z be an element of U. Right? And then I want to show that there exists an open set contained between Z and U. Oh boy, and then, so I have a Z. And since this is a locally path-connected space, every element is contained in an open path-connected neighborhood, right? So since X is locally path-connected, there exists an open set path-connected set. I'll call it B because I'm thinking of the stuff that I get from the local path connected condition as a basis. Right? There exists an open path connected set B such that Z is an element of B. And now all that's left to show, that B is contained in U. So to show this, I take an arbitrary element of B and I show that that's an element of U, right? So let W be an element of B. Then, since B is path connected, W is connected to Z via path, right? Also, Z is connected to X by the definition of U. So since this is a equivalence relation, this is what I just said, right? There exists a path from W to X, i.e. W is an element of U. Yeah. So there exists an open set between U and Z, and since U is arbitrary, U is open. And then the last thing that I should say is that the proof that V is open is similar. Right, you choose an arbitrary element in V, right? You say that, hey, since I'm locally path connected, right, there's a path connected set around V, and this can't be in U or overlap with U, because then I could concatenate a point in V as a path to X. Right? I guess that I can draw a picture for V, right? You choose an arbitrary point in V, you choose a B around that point V, and this can't overlap with U, U's over here, because if it did overlap with U, I could take a path into my open set here and a path here, but then I'd connect X via a path into V, and that can't happen the way that V is defined, right? V is all the points that you cannot connect a path to X, right? So this is similar, and perhaps I should leave it as something to think about. Although if there are any questions about how V works, we can do it. There's a message in the chat. Okay.
In that second to last line, should that be W is in B, is in U?
Yes, that actually should say W. Thank you. Yeah, thank you. Are there also, Shanna, your cat is adorable. I'm very glad that there's cat on stream.
That's Natasha. She loves your voice. She's used to hearing me talk about math. She's excited.
Fantastic. Okay. Yeah. So yes, that should be W as an element of V, which is contained. Yeah, I used to do this proof by writing out, therefore there's a path from blank to blank, therefore there's a path from blank to blank. But you know, after you do it many, many times, because someone keeps asking you to do it, right, you eventually find a more concise way to. Right, cool. Yeah, it's hard to draw pictures for proofs by contradiction because, like, you know, you're trying to get a contradiction. So any way that you draw the picture is not supposed to work. But it really is like, hey, right, if this left side is all the points that I can get via path here, and this is all the non-points, then anytime I put path connected open sets around, I can't have a path connected open set which crosses this line. Okay, that's essentially the entire idea behind this proof, right? That locally path connected gives me a basis of path connected sets, right? And that basis has to respect path connected components. Right? That's okay. So then I should scroll down instead of delete, which is what I'm used to doing. So part 5 has a second part. which says that prove that any open connected subset of a locally path connected space is path connected. Well, all that I have to do is show that an open subset of a locally path connected space is locally path connected. And then I can just use the first sentence, right? Because a connected component of a locally path connected space is a connected locally path connected space, as long as, right, it inherits the subspace topology, right? So right, does that make sense, or should I repeat?
Sorry, can you repeat that?
Yeah, repeat or write is excellent.
Yeah, okay, I can do that. So yeah, so the second sentence states that show any open connected subset of a locally path connected space is path connected. Okay, so this proof is much shorter than the above proof, right? Because we get to use part A to prove part B, right? So let X be such space and Y, a subset of X, be an open connected subset. So an open subset, right, then Y is locally path connected, right? Because being locally path connected, to use a phrase that Wilhelm loves to use, is an open condition, right? It's a local condition, right? Locally path connected says that you have a basis of path connected sets, right? So an open subset, right, it inherits the same topology. You just restrict your basis to that open subset, right? And then you get a locally path connected base, or a path connected basis, right? So then Y is locally path connected, right? And Y is connected by assumption. So by first sentence, Y is path connected. Right? That's what we just proved, right? We just showed that a locally path connected and connected set is globally path connected. Right? Yeah. So all that this second sentence is saying is that, like, hey, if you are a locally path connected space, right, its open connected subsets are globally path, or the globally path connected subsets are also globally path connected, because they're like, you could have a globally path connected subset that's like closed or something. Yeah. As a question, why does this fail if I get rid of the word open?
Well, we use the assumption that it's open because for what it means to be a basis is that any open set is a union of basis sets, but that doesn't necessarily hold for arbitrary sets.
Right. Yeah, it's because, well, I need that my subset is locally path connected. So for example, let's see, can I think of a sly thing which is locally path connected but not globally path connected if I take a non-open subset?
I always forget, is the topologist sine curve.
Yeah, that's the one that I was just thinking of right now, but that might be the other example of this thing. Right. Yeah, but I suppose the topologist sine curve is always worth talking about. So for those of you,
can you say that one more time? So what fails if we did not have the open condition, then you wouldn't have your basis condition, right?
yeah,
Okay.
yeah, your subspace might not be locally path connected.
Right.
Because if you just choose an arbitrary subset, even if it is connected, okay, it might be connected in a weird way.
Right.
In a way that prevents you from making paths. Right? Yeah. And the topologist sine curve might be a thing. And since someone brought it up, it's certainly worth talking about. So what the topologist sine curve is, we take the graph of the function sine of 1 over x. And there are a couple of variations of this. Union the set of points 0, comma y such that y is between -1 and 1. Okay, so this part, and maybe I should put brackets like this. It's the graph of this function union these points. Right? Sometimes union some other stuff, but I'll talk about that in a second. So if I take the sine curve, it does the oscillation thingy. Right? And then I have -1 to 1 here. And this other stuff, sometimes we attach this tail here to here. Right? And the reason that we do that is that we have a globally path connected space, which is not a locally path connected space. So in fact, this is an example of my condition because this is not an open subset of R2, but it is a connected subset of R2 because it's globally path connected, but it's not locally path connected. So this, hey, Anthony was correct in that there's a version of the topologist sine. Sorry, when you first said topologist sine curve, the one that I was thinking of was the disconnected one, right? Where the, yeah, or sorry, not the disconnected one, but the non-path connected one. But I guess both work. Right? Yeah, so the reason why is because even if I remove, okay, so there's two versions of this. So let me highlight. So there's these two versions of the curve, and it's nice to know their properties. This is connected. It's not path connected, and it's not locally path connected. Whereas this one over here is connected, path connected, but not locally path connected.
I'm sorry, you might have said this, but are these both the topologist sine curve or? is
Yeah, so the
one with
topologist
red?
sine curve is anything that looks like this stuff. So the left-hand side, anything that contains the left-hand side is the topologist sine curve. Right?
Okay, cool, perfect.
Yeah, yeah, and it just depends on what you need, right? Like if you need a non-path connected example, you use the one on the left. If you'd like your example to be path connected, then use the one on the right. But yeah, so if you're looking for an example of a space which is path connected but not locally path connected, then you use the one on the right. But if you don't need path connectedness, then you can use the one on the left. And so maybe if I was being more specific, I'd like restrict the domain here between like open at 0 and like closed at x equals pi or something. So that way I could like explicitly say that it ends here or something. But the right side of this doesn't contain the topological properties that we care about. So even if this like extended this way and I had like a, you know, a tree behavior here or something, it wouldn't change the topological property.
And this one on the right is not locally path connected because why?
Yeah, so great question. So if I draw a this zoomed in, so I don't care about, so this comes in and it gets closer and closer and closer and closer and closer.
Mhm.
The idea is to take a point. You're not going to let me change colors because you're a terrible program. If I take a point here, right, and then the open set that I want you to find a open path connected component around looks like this, right? It's like a little open box like this,
Mhm.
right? Then this does not contain an open path connected set, right? Because it will always at minimum contain this path component and this path component, and those are not open subsets, right?
Perfect.
Yeah.
Thank you.
Those are not path connected, right? Yeah, there's no way to connect those with any open set that you stay inside the box with. Yeah, they're open in the subspace topology. So that's not the reason why it fails, but it fails because, yeah. So this is not path connected. And that's why it's not a locally path connected space.
So then the one on the right is path connected because of the red part, obviously.
Yeah, it's globally path connected because if I want to connect my left edge with any point on the curve, I can just go backwards around the curve, right? And right, I go backwards. By backwards, I mean like this way. And then eventually I go through the red bit and then I go back up to this point. Like, hey, I found a global path. But if I restrict to a small neighborhood, even around those 2 points, right, then I'm not path connected anymore. Right?
And that is what means that we're not locally path connected, is when you restrict.
Exactly.
Okay. Okay. Cool. Thank you.
Yeah. So this is a nice example to keep in the back of your pocket every time you come across one of these theorems that's like, hey, this covering space theorem happens for like a locally path connected space, or an open subset of one of these things, or every time you're just like, why do we need both of these things? It's because something goes wrong with these two examples. Okay, so let's look up. So I had 5/6. I don't know, are there any? I just kind of wrote down numbers that people thought. So are there any of these that people have strong opinions about? If like Jacob, do this one next.
I would just say one of the coverings. So maybe I like the coarsest topology. So either like 9, like, I don't know, 8, 9, and 11, I'm pretty strong about, but whatever you think.
Okay.
Or like 9, maybe 9 and then 11, 8. I don't know.
Okay, yeah. So yeah, do I remember how to do the second part here of 9? Oh no. Right. Yeah, it's the second part of 10. Okay, yeah, let's do 9. Okay, 9. So right. Okay, so I love this kind of stuff because I love the let's put specific topologies on things kind of problems. Okay, so what we're looking at is we're looking at 2 projections, right? Which I just signified as pi sub I, but there's like pi 1, which is projection onto the first coordinate, and pi 2, which is projection onto the second coordinate, right? So pi 1 of a pair x1, x2 just maps to x1. Pi 2 of the value x1, x2 just maps onto x2. And so okay, I'm trying to remember how this is done in a clean way. Right, so let's let x1, x2, comma, sorry, that's not x1 comma x2, x1 cross x2 comma tau product be the product topology. And showing that this is the coarsest topology that makes this function continuous means that I want to show two things, right? So the two things that I want to show, the first thing is that pi1 and pi2 are continuous with respect to the product topology. Right? And the second thing is that if I take x1 cross x2 comma tau with some other topology such that tau is strictly coarser, which means tau other is strictly coarser than tau product, yeah, then either pi1 or pi2 are not continuous with respect to the other topology. Although there might be a way.
Wouldn't it be easier to show that if you take any topology such that they're already continuous, then it contains the product topology?
Yeah, I was going to say, yeah, I was in the middle of saying the sentence, it might be easier to show that. Yeah, or we'll do what Zachary suggested, or if T other is such that pi1 and pi2 are continuous with respect to tau other, then the product topology is coarser than tau other. And this second one, the more that I look at it, might be the way that we do this, because that seems like something which is more straightforward, because that says, hey, I know something about this topology. It contains the things which make this continuous, and hopefully the things that make this continuous are are exactly the things that generate the product topology. I guess so the third way that combines both of these things might be to show that those topologies are exactly the same, right? But okay, so let's start working on this first statement that pi1 and pi2 are continuous with respect to the product topology. So the way that I show that something is continuous with respect to the product topology is I want to show that pre-images of these open sets are open with respect to whatever topology I put on my space. Right? So this first statement is quite simple. So the first, right, is to say let U be an open set of, without loss of generality, x1. Then the pre-image of pi1 of U, right, is just equal to U cross x2. which is a basic open set for the product topology. Because recall, I put 2 R's in here. Recall, if I take U cross V such that U subset of X1 is open and V a subset of X2 is open, that this here, one step down, right, is a basis for the product topology on 2 sets. Right? So U is certainly open in X1. That's how I defined U. X2 is open in itself. Okay? So this product is one of the elements in the basis for the product topology. Okay? Cool. So that proves statement 1. Statement 2, we'll try using Zachary's version, because I think Zachary's version is going to be better, right? So I want to say, so the way that the second statement is going to go using this version is I want to show, hey, if these pre-images are open, what I'm going to want to do is I'm going to want to generate this basis that I just created here. Right? That I'm going to be able to show that all of these basic open sets are open in whatever other topology, right? So assume pi I are both continuous in the other topology. Also, I understand that my handwriting is not great, and I'm trying to run the line between writing fast and writing legibly. And if I ever go too far away from the legible side, let me know. I'll write slower and more legible. Then we're going to let U be open in X1 and V be open in X2. And I want to show that U cross V is open in tau other, because then the basis for the product topology is open in tau other, and that will imply that the product topology is contained in my other topology. So this entire line is the want to show statement, I guess. Right. So once I show that this cross product is open in the other topology, then I have the basis for the entire product topology. Right. So that means that my entire product topology is contained in my other topology. This is what? Okay, this isn't lemma 13.3 in Moncrief's, but it's almost lemma 13.3 in Moncrief's. Okay, so pi 1 inverse of U is equal to U cross X2, and pi 2 inverse of V is open to X1 cross V. These are both open in the other topology by assumption. So their intersection which is equal to U intersect X1 cross X2 intersect V, which is equal to U cross V, is open in the other topology. And that's exactly what I wanted to show. Yeah, so you're right, Zachary. That was a lot easier than the first statement that I just said. Glad we did it that way. Questions, comments, or concerns? Or complaints? I'll take those too. But you always pause between concerns and complaints, just in case someone has something that's not a complaint.
No, I think it's excellent.
Yeah, hopefully this was clear. It took a while to get there, but okay, cool.
Do you think we could tackle a little bit of 8? Because now you've, I don't know, the covering looks a little better.
Yeah, okay. So B is compact when E is compact. Okay, yeah. Yeah, I don't know because we're supposed to end in 4 minutes. So maybe we can do just this first bullet point of 8. But oh, okay, yeah, the difference between 2 and 3 is okay. Let's just do the first part of 8. We can go back to other ones on later days, I suppose. Okay, so let's show that B is compact when E is compact. So suppose E is compact, and let P, a map from E to B, be a cover. Let script U be an arbitrary open cover of B. Okay, so what I would like to do is I'd like to just take the preimage of all of these sets and then say that E is compact. So these preimages restrict to a finite collection and then just push that finite collection down. All right, but I can't do that, not yet. What I need to do, right, the key behind this first point is that I need to refine my open cover U into evenly covered neighborhoods. Right. That's the key behind this problem, is that you do some sort of refinement to is that you do some sort of refinement to like evenly covered neighborhoods, and then you can do this problem that way. So we're gonna let V be a refinement. What do I mean by refinement? So let's see, for every X in B and U, let's see, there exists U in script U such that U contains X. Take V to be equal to U, intersect an evenly covered neighborhood of X, right? Then script V is the collection of such capital V's. Okay, so what did we do here, right? So here I have B, E lives up here, and I prefer not to put constraints on what E looks like, right? It could be that like my open cover of B is like just B, but then I could just take itself, right? But you know, it could be that like U looks really bad, maybe it's even like disjoint or something, and I take a point X and I say, hey, the nice open sets in a covering map are the evenly covered ones. So my evenly covered neighborhood, the arbitrary one that I pick, might be out here. but any open subset of an evenly covered neighborhood is still evenly covered. So if I take the intersection of U and an evenly covered neighborhood, I get another evenly covered neighborhood. So I take this intersection that I drew here. Colors would be good, but I'm running out of time. And that's what I'm going to do here. Oh boy. Boy, did I even have to do this? Or is this something that I have to do for part 2? Now I'm wondering. No, I think that you might just be able to take the preimage of your open cover and say, hey, there's a finite subcover, and then the images of those preimages are still cover. Yeah, because you cover E and the map is surjective. So yes, I don't need this to be a refinement. I apologize. So let's just fix this. We'll still use script B. B defined by script V is equal to the set of all pre-images of U such that U is in my open cover. Right. This is an open cover of E because right, covering maps are continuous, and this is just the pre-image of, right? Yeah, so yeah, this statement is just that the image of a compact set is compact under a continuous map. I don't need any of the covering space. Yes, this, okay. Okay, yep, this is an open cover of E. So there exists a finite subcover, say I equals 1 to n, contained in script V. I can make my script V look nicer. Then the claim, right, is that the set of UI, I equals 1 to n, where P inverse of UI is equal to VI. This is a finite subcover. Of script equal. Right. And it's not the same as saying that, hey, the images of the VIs are the UIs, because that might not be true, right? You might have a, oh no, yes, that is true because we define it with preimages, so never mind. Yeah. Yep. And essentially the reason why this claim is true is because, right, every point of the pre-image, E, right, Y, for all B and B, there exists E and E such that P of E is equal to B. So since there exists I such that VI contains E, P of VI, which is equal to UI, contains B, which is equal to P of E. Cool. So this finite collection is a cover, and it's a sub-collection because that's how we defined it. Okay, so this was a little off rails because I was like, why did I, how? Because I was like, I put this in with all the covering stuff, so you probably need the covering stuff. But this is actually just a fact about any continuous function, right? For any continuous function, the image of a compact set is compact. C number, I've probably assigned this as one of these. Yeah, C number 4. Okay, that's one of the things that I just said. Like if you have a continuous map with a compact domain, then the image is compact. Okay. And so that's actually all that 8.1 was saying, that like, hey, you have a compact domain, it's a continuous function, so your image is going to be compact. And I should have just cited that when I looked at number 8. I should have been like, oh, this is a prior problem. You just get this for free because covering maps are continuous. We'll probably end here today. We'll start off Thursday by talking about covering maps, because you asked about covering maps and we didn't actually do a covering maps problem. We just did a continuous maps problem. So we'll probably do the rest of question 8. If anybody has any other recommendations or problems that they'd like to go over on Thursday, feel free to let me know now or send them. Otherwise, I think that's going to be it for us for today. Happy studying.
Jacob, could I just have a moment of everyone's time?
Sure.
I'm moving back to Riverside, and I'm looking for either a place to live or people to live with. If you have any info or any openings or anything at